I might just need to ask, how is everybody? Let's start with Katli. How are you?
I'm fine, thank you, sir. And how are you?
I'm doing very well, thank you very much. Letabo.
I'm doing good, so thank you.
Thank you very much. Ladies, I am not going to keep you long. We will do this session until 1845, and we are only going to look into electromagnetic radiation and just perform or do a couple of problems that relates to that, perform certain calculations, but basically there isn't much, or there isn't any much thing to worry about with electromagnetic radiation. It's just an issue of what is it that we have, what is it that is given, and then we will be able to explain all the concepts. Ladies, without wasting any time, let's go straight into it. Now, with electromagnetic radiation, what is critical is just to understand the nature of the electromagnetic wave. Now, with an electromagnetic wave, you have accelerating charges, which now are perpendicular to the direction of the motion. And that will now create what we call the magnetic field. And this magnetic field is the one that will now generate the electromagnetic waves. Why is that the case? That is the case because you have now the magnetic field, the electric field that is now acting perpendicular, and that now relates to electromagnetic wave being generated. So electromagnetic wave has what we call dual nature of electromagnetic. Dual nature of electromagnetic radiation. What do we mean by dual nature? Ladies and gentlemen, it can act as a wave. At the very same time, it can act now as a particle. So this nature of an electromagnetic radiation allows us to actually use electromagnetic waves for a different sets of life challenges or life situations. Why is that the case? That is the case because in this instance we can easily say behaves like a wave. In this instance we say behaves like a particle. And if it behaves like a particle, ladies and gentlemen, we are able now to say if it is a particle, we can treat it with what we call energy of a photon. Because, ladies and gentlemen, once we talk of photons, these are just small particles of the radiation, and we call them photons. So a photon, ladies and gentlemen, is just a small particle which consists now of small particle which consists of electromagnetic radiation. Very, 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 very important. That is the reason why, ladies and gentlemen, when you check at 5.3, we have now what we call electromagnetic spectra. Now, with the electromagnetic spectrum, what are we expected to know? We are expected to know how each wave behaves. We are expected to know the applications of each wave that is given in the spectra. For you to be able to remember, you can develop any other analogy using the first letters of each. There are so many analogies that are available for us to actually understand and remember the electromagnetic spectra. We will get into the uses and the functions of each and every wave that is given in terms of the electromagnetic spectra. Why do we need to do that? Remember, it behaves as a wave, it behaves as a particle. So that dual nature of electromagnetic radiation allows us to treat it as a wave and also allows us to treat it as a particle. So that nature makes it possible for it to function according to all the functions that we are going to look into. Ladies and gentlemen, here are few properties of an electromagnetic wave. And with these properties, what are we going to do? We are just going to say the very first one is electromagnetic waves have a constant speed of 3 multiplied by 10 to power 8 meters per second. And this, ladies and gentlemen, is what we call speed of light. So the speed of light is constant for all the different electromagnetic waves in the electromagnetic spectrum. All of them will have that. Do not need a medium for propagation. Why do we say so? They do not need a medium because remember, ladies and gentlemen, they travel anywhere. For it to be a wave, it must travel in a medium. For it to be a particle, it can travel anywhere. So generally we say they do not need a medium for propagation. Remember when we spoke of longitudinal waves, when we spoke of the transverse wave, we said they must travel in a medium. But with electromagnetic waves, ladies and gentlemen, they do not need to have any medium for them to actually move. Have all properties of the waves. All properties of the wave, they will mean what? They will have your amplitude, they will have your frequency, they will have your wavelength. Why, ladies and gentlemen? Because these are properties of the wave. Properties of a particle, then this new weight that is coming up. What is that new weight that is coming up? That new weight, it is now a photon. Let's write it down and say this new weight, it's now a photon. Why? Because a photon, let's write it down. At A, we have now a new weight which is called a photon. What is a photon, ladies and gentlemen? It's an energy packet. An energy packet of electromagnetic radiation. So this photon, ladies and gentlemen, it's the one that allows us to treat it as a particle. That is now very, very, very important. Then the other property is it is a transverse wave. So the fact that we did now transverse waves in full totality, one fully understand basically what is a transverse wave. So because it is a wave, ladies and gentlemen, we can be able to relate the frequency, wavelength to the speed of the wave. But however, in this instance, we are only going to use it in a sense of doing what? In a sense of looking into the equation C is equals to F lambda, where C it is the speed of light, F is the frequency, and then wavelength it's just lambda in meters. So basically, because of this property of the wave itself, it allows us to actually look into performing calculations that are going to relate to electromagnetic radiation. But now let's check, ladies and gentlemen. There are a lot of important things that we need to know. What we need to know is what we call conversion at number B. Conversion factors or conversion factor. They call it me na P. This is for milli, this is for micro, this is for nano, and this is for pico. And this here, ladies and gentlemen, it is just 1 multiplied by 10 minus 3, 1 multiplied by 10 minus 6, 1 multiplied by 10 minus 9, 1 multiplied by 10 to minus 12. And let's write it in terms of symbols. This one will be something like macro. Let's just do this. And this one will be nano, and then this one will be just pico. Ladies and gentlemen, all these conversion factors are needed because remember, when we work with this electromagnetic waves, at times they are very short such that they can give us a very high frequency. So the representation thereof will be given in a form of conversion factors. So it is important for us to basically understand how to convert. So let's look into the example that has been given to us. An infrared with a wavelength of that. So lambda is equals to 3 micrometer. And that, when we convert, we come to our conversion factor. It will be 3 multiplied by this factor, then it will give us the correct conversion factor. We cannot perform 3 micrometer. This is just equals to 3 multiplied by 10 to minus 6 meters. Hence, ladies and gentlemen, it is important for us to use the analogy of Mimina P. Mimina P, it is just an analogy for us to remember all the conversion factors that we are going to need. Then the question says calculate the frequency. Now for me to perform a calculation, NP, only two variables are needed to perform a calculation all the time. Because when you check all the equations that we are going to work with, they only have 3 variables. So for us to perform a calculation, we actually need to have 2. But at times it becomes a multi-step. When it is a multi-step, it means you must use 2 different equations to answer the same question. Now, what else do we need? We know C is given, which is a constant, 3 multiplied by 10 to power 8 meters per second. The formula, F is equals to C over lambda, and this is just equals to 3 multiplied by 10 to power 8 divided by 3 multiplied by 10 to negative 6. Then F there, ladies and gentlemen, is 1 multiplied by 10 to the power 14 hertz. Very important for us to actually perform such a calculation. Kindly questions, please.
No, sir, I don't have any questions
Thank
so
you,
far.
Letabo. Any questions, please? I believe there's nothing. Then let's move into 5.5. Ladies and gentlemen, at 5.5,
No questions, sir.
thank you very much, Letabo. At 5.5, ladies and gentlemen, we have penetrating ability. What is penetrating ability? Remember, these waves, they do not travel in any media. How is it possible for us to actually tell that the people next door are talking, even though we do not see them? It is because of the type of wave which is propagated by the audio, maybe from the TV or from the radio itself. So that nature refers to penetratability of what? Of the wave itself. So when we move from infrared to gamma rays, we have now an increase in penetrating ability. So it means gamma rays will have a higher chance of penetrating through a certain particular media. Better than what? Better than infrared. And obviously anything else after infrared, it is your radio waves and your microwaves. So obviously everything after before infrared automatically will have a lower increasing, a lower penetrating ability as compared now to gamma rays, because gamma rays now is what? It's the last one within the spectrum itself. Now, ladies and gentlemen, we also need to know the type of radiation as well as the functions thereof. Very, very, very important. Now it says if I have the radio waves, they are used for radio and television broadcast as well as radio telescopes. However, there's a disadvantage in everything that we do. There's noise pollution due to radios and TVs that are too loud. So if the people are now misusing the radio waves because of watching TV and radio, playing it too loud, that now influences the noise pollution, and that becomes now a disadvantage. We have microwaves. And these are used now for telephones connection, communication satellites, cell phone connections, radar systems, radar traps, and even in microwave ovens. So it means when we start communicating, and this call also that we are in this particular meeting, it is broadcasting because of now what? Of the microwaves. So the microwaves, ladies and gentlemen, are there to assist with now telephone connections, to assist with communication satellites, cell phone connections, radar systems, and radar speed traps. If you remember well, when you go and pass Aljo's, there was a nice smaller camera for people that are driving at high speed. On the ground, you had stripes connected to the road that feeds the camera on the side of the road. That was also using microwaves because it is a radar speed traps. So it means we need now this type of electromagnetic radiation waves in order for us to perform some of our daily duties. However, everything has a disadvantage. The use of cell phones can be addictive, which could lead to lack of productivity. It is true. People are able to sit and watch their phones, TikTok for a very long time. That now hampers what? Productivity. That hampers what? The focus of us as individuals to actually interact with one another. People rather sit in their bedrooms and look at their phone instead of communicating with one another. So the cell phones can be very, very addictive. What about infrared, ladies and gentlemen? Keeping food warm in a takeaway restaurants, remote control of the TV, optical fibers for telephones and internet connections. Some snakes hunt their prey with an infrared at night. So infrared, very, very, very important. Used by poachers and soldiers for tracking at night. So it's very easy. When it is a time for war, there are guns that have this infrared. When they see the prey or a poacher or somebody like that, what do? They basically just use that infrared to actually shoot the right target. So that becomes now a disadvantage. Visible light. Visible light is what we call Roy G. Beef. That is now from grade 8. Red, orange, yellow, green, blue, indigo, and violet. This visible light. Objects reflect light, which allows us to see them. So for us to see objects, there has to be light that is transferred from the object to us. So if it wasn't of visible light, we will not be able to see any object. That is the reason why when it is very dark, ladies and gentlemen, you don't see anything. But once it is daylight, you are able to see other objects around. Why? Because of the visible light. It is important for photosynthesis, and fortunately enough, it does not have any disadvantages. X-rays are used now for CT scans, security scanners, medical images penetrate soft tissues but not the bone. But we still have gamma rays, which will be now important for radiation of cancer. And it says is released during nuclear reaction and can cause damage resulting in death of people, animals and plants. So when you are going for a radiation for them to kill your cancer cells, they must just give you the right amount of exposure. If they don't give you the right amount, ladies and gentlemen, that will result into you the parts of your body, the organs, to be exposed to very high radiation. So that will also influence, ladies and gentlemen, will also influence your outcome of the radiation itself. Now, there's one thing that I want me to emphasize here. My emphasis will be on gamma rays. Very, very important. Gamma rays have now highest frequency, short wavelength. Very, very, very important. What about radio waves? Radio waves, longest wavelength, lower frequency. We need, ladies and gentlemen, to understand this relationship. So when you move from radio waves, let's write it in this manner. Let's have R and let's have G. R is for radio, and then this is now for gamma. We say long wavelength, low frequency, and we say short lambda, high frequency. That is now when you move into this particular direction. Let me take now a nice arrow to explain that. That is now what happens when we refer to the wavelength as well as the frequency. So the radio waves will have the longest wavelength but with low frequency. So the reason why it is possible for us to work with gamma rays for purpose of radiation is that they have a higher frequency. Higher frequency, shorter wavelength. That is now very, very important, ladies and gentlemen. With that being said, it means we can now go and look into possible ways of answering questions that relates to this. Why possible questions, ladies and gentlemen? Possible questions because when you look into this, the only thing that is left is now for us to talk of Planck's constant. And what is a Planck constant? Planck's constant symbol is H. Value is something like 6,63 multiplied by 10 to power negative 34 joules second. Now this brings us to calculate the energy of a photon. The equation is E is equals to HF, where E is now what? Energy of a photon. H, it's now Planck's constant. And what is now the SI unit for the energy? The SI unit, ladies and gentlemen, is J for joules. However, we have F, which is now for the frequency. So frequency, it is measured in hertz, ladies and gentlemen. One can easily say, but F is equals to C over lambda. Then one can say E is equals to HC over lambda. But ladies and gentlemen, let's be on the lookout to see this equation. It is not in the formula sheet. Not in the formula sheet. So what does that mean? It means, ladies and gentlemen, we must use equation number 1 and equation number 2 independently. If I am going to give you marks for performing something like this, it means I must be in a position to actually award a mark for equation number 1 and award a mark for equation number 2. I said some questions will be straightforward, which will just need one equation. However, this is an exam. So what do we do in an exam? In an exam, we are going to request you or try to give you questions that are going to ask you for a multi-step. What is a multi-step, ladies and gentlemen? A multi-step is now what? It's now using of two equations to get to the correct answer. That is very, very important. Then with that being said, ladies and gentlemen, let me give you your 50 seconds to digest everything, and we can close today's session with one example on how to use Planck's constant. Thank you very much, ladies and gentlemen. Let's look now into this example that we have here. It says infrared rays with a wavelength of 3 micrometer are released by the sun. The frequency is given as 1 multiplied by 10 to the 14. Calculate how much energy the infrared photons have. So this one is easy. What do? We write down the data given. I have lambda, which is just 3 micrometer, which is just equals to 3 multiplied by 10 to negative 6 meters. Hence, ladies and gentlemen, we need this convention factor. So this is very, very important. If we are given the frequency, sorry, we are given now the frequency, which is 1 multiplied by 10 to power 14 hertz. But I know the equation that says E is equals to HF. Why are they giving me the lambda? It's just to confuse me. Can you see that? Because I don't need that. Because Planck is a constant with 6,63 multiplied by 10 to negative 34 multiplied by 1 multiplied by 10 to the power 14, and the final answer, ladies and gentlemen, it will be something like 6,63 multiplied by 10 to power 20 negative 20 joules, and that is now our final answer. Ladies and gentlemen, I am going to give you some time, something like 3 minutes, for you to actually do number 2. Feel free to send your answers. Thank you very much, ladies and gentlemen. Let's start sending the answers so that we can conclude today's session. Thank you very much. Thank you very much. Ladies and gentlemen, let's look into it. Calculate energy of the photon. So basically they want now E. H is a constant, ladies and gentlemen. It is always given 6,63 multiplied by 10 to negative 34. We are given lambda, which is the wavelength, 410 nanometers, which is equals to 410 multiplied by 10, conversion factor minus 9 meters. Now when I look into the energy of a photon, E is equals to HF. But now it becomes problematic for me because F is not given, ladies and gentlemen, not given. So what can I do? But F is equals to C over lambda. Ladies and gentlemen, what is C? C is equals to 3 multiplied by 10 to power 8 meters per second. It is also another constant. So this is another constant, ladies and gentlemen. So I can easily say E is equals to HC over lambda. The fact that the formulas, these two formulas, number 1 and number 2, will be given, ladies and gentlemen, in the formula sheet. So Letabo, don't confuse the formulas. Just check that if you have F that is not given, then F is equals to C over lambda. Then, ladies and gentlemen, we can just substitute all the information given, and that information is just 6,63 multiplied by 10 to negative 34 into 3 multiplied by 10 to power 8 Letabo. C is a constant. It is given in the data sheet. Divided, ladies and gentlemen, by 410 multiplied by minus 9. Currently, every information was given. The only factor was, but the equation says E is equals to HF. So if E is equals to HF, what must happen now? I don't have F. What else can I use? Remember, we said we need only 2 variables for us to perform a calculation. And the final answer, ladies and gentlemen, is 4,85 multiplied by 10 to negative 19 joules. And that is how we get now to the correct answer. Katli, reflections, please.
So I think I think before I was a bit confused, but after a while, I think I got what was said.
Thank you very much. Letabo, inputs, please.
Yes, I understand where I went wrong. I just used the wrong formula.
100%, because now you did not refer to the formula sheet. Hence, I said, ladies and gentlemen, go to the website, download any paper of grade 10, you will get your formula sheet there. The formula sheet is not a scandal, it will be given. So, why not have it already with you such that you can be able to practice day in and day out with it. Ladies and gentlemen, with that being said, tomorrow we are meeting at 7:30 to 8:30 because tomorrow it is a grade 11 class. The arrangement was only for today, but I will still keep you in touch. Ladies and gentlemen, with that being said, thank you very much and have a lovely evening.
Thank you,
Thank
sir.
you, sir.
Bye.
Bye, sir.